In this study, we are going to solve the heat conduction equation, which is a parabolic PDE, and obtain the solution temperature with respect to x dimension and time. So the temperature here can be written in the mathematical notation TIL, where your L is equal to the index number of the time. Then you have the L equal to 0 sample, first sample, second sample, third sample of the time. And if you write the time index to be L, it means the current sample of the time. L minus 1 means the previous one sample of the time. L plus 1 means the future one sample of the time. So same concept can be applied to I, where I is equal to the index number of the space x. I equal to 0 sample, first sample, second, third of the x. And if you just write I, it means the current sample of the x. I minus 1, previous one sample of the x. I plus 1, future one sample of the x. In this case, assume that you have a root with 4 meter length in the x direction. And then let's say we measure the temperature at this 5 point. Then we can let the x0 to be the first point, x1 to be the second point, until the x4 to be the final point here, where we use the notation xi, and your I is equal to 0, 1, 2, 3 until 4 in this case. And you can find the step size delta x to be equal to 1 meter, which can be found by using this formula, where your total length is 4 meter, total number of points is around 5, minus with 1 here, so with that you obtain 1 meter. Therefore, we know that your location for the x0 is equal to 0 meter here, the x1 is 1 meter, x2 is 2 meter, x3 is 3 meter, and lastly your x4 is 4 meter here. We find the temperature at 5 locations only, which is x equal to 0, 1, 2, 3, and 4. The temperature at these 5 points will change with respect to the time here, where you can see at initial time equal to t0. The initial condition is given by txt equal to 0 degrees Celsius, which means for all the point x, your initial temperature is 0 degrees Celsius. So imagine that all the point here, initial condition, the temperature is 0 degrees Celsius. Imagine that at t greater than 0, then you apply the boundary condition, where you can see the x equal to 0 for all the time t, you get 100 degrees Celsius. So x equal to 0 means this point, so your temperature should be 100 for all the time. And then at x equal to 4, for all the time, you get 0 degrees Celsius. So x equal to 4 is this point, so for all the time, you should get the temperature to be 0 degrees Celsius. Consider the initial condition and the boundary condition. You obtain this information. Your task is to find the temperature at this region, which is the temperature at point x1, x2, x3 at time t1. And as time passes, you are going to find the temperature at point x1, x2, x3 at time t2, and so on. As you can see, the time is changed from t0, t1, t2, t3, and so on. And the difference between two times is equal to the step size delta t. And we want to find the temperature over the time t L here, where the L is the index 0, first sample, second sample, third sample, and so on. You can use the explicit scheme to find the information here, which is the unknown temperature at point 1, 2, 3 at time equal to T1, T2, T3, and so on. To find the temperature at xi and the time L plus 1, you need these three information in order to compute the temperature at this point in the explicit scheme. For example, to find the temperature at x1 and time t1, then we can let T11 to be equal to TIL plus 1, where your I is equal to 1 and your L is equal to 0. By using the I equal to 1, L equal to 0, we can find this to be T0, 0, this to be T1, 0, and this is T2, 0, which is the temperature at these 3 points. By using the explicit scheme, we can find the temperature at T11 here by using these 3 information. By using the same method, let's say you want to find the temperature at T21 here, then you need these 3 information to find. So if you continue to find the temperature at T31 here, you need these 3 information. To find the temperature xt from the parabolic PDE, we use the center type of finite difference method to find the second derivative of the temperature with respect to x to be this answer, and we can use the forward type of finite difference method to find the first derivative of temperature with respect to time to be this answer. Then substitute these 2 formula inside the PDE equation and you should be able to obtain this answer. Let's multiply the equation with delta t on both sides. Then delta t here can be cancelled. You need to multiply delta t on the left hand side. Then you add the t, I, L on both sides so that this term can be cancelled, and then you have t, I, L here. So with that, you success to obtain the TIL plus 1. So this is the equation after you rearrange it. Delta t multiplied with k divided by delta x squared is equal to lambda here. This equation is the numerical modeling result of the parabolic PDE, where we can use this equation to find the TIL plus 1, which is located here. And to find this, we need the TIL, which is located here, Ti plus 1 L, which is located here, and lastly, Ti minus 1, which is located here. This is called the explicit method because we can explicitly express this equation on your left hand side to be the unknown Ti at future time L plus 1. Normally, these 3 temperature can be known in advance because the temperature is at point xi, xi minus 1 and xi plus 1 at the current time, TL. Therefore, we can use this equation to find the unknown here. The selection of the lambda constant is very important to control the convergence and stability. It depends on the selection of the delta t and delta x. So ideally, delta t, delta x need to be very small, approximate to 0. However, this condition cannot be achieved in many cases because if you choose the delta t, delta x to be very small value, then the computational time will be significantly increased. On the other hand, if you choose the delta t and delta x to be a large value greater than 0, then the accuracy will be affected. So it's very important to choose a correct lambda in order to obtain accurate solution here. In this example, we are given the thermal conductivity of the aluminum rod, which is equal to 0.49, and the density of the aluminum is given by 2.7, and the heat capacity is 0.2174. So we are going to find the temperature distribution by assuming the delta x equal to 2 cm and the time is changed with respect to 0.1 second. The initial condition is given by this, where you can see the length of the root is x from 0 to 10. So that means the total length is 10. Since the total length divided by n plus 1 equal to delta x, where the n is the total number of points of the root, so you can find the n here. So let's substitute the total length to be 10, delta x to be 2. So from here you obtain your n plus 1 equal to 5 and your n is equal to 6. With that, we draw 6 points here and the delta x is equal to 2 cm between the points. We are going to find the temperature at point 0 here, point 1, 2, 3, 4, and temperature at point 5 here. The boundary condition is given by this, means that at x equal to 0 for all the time the temperature is 100. So it means that at x equal to 0, your temperature T0 for all the time will be equal to 100. So we should expect that at this point, the temperature will be always equal to 100 degrees Celsius. From the second boundary condition, you know that at x equal to 10, which is your x at 0.5, the temperature at 0.5 here for all the t will be always 50 degrees Celsius, which means at this point the temperature will always be equal to 50 degrees Celsius at any time. From the initial condition, you can see that for all the x, means for all the points here, at t equal to 0, your temperature is equal to 0. So means that at t equal to 0, your temperature will be equal to 0 degrees Celsius. This is the PDE for the heat conduction problem here. And you can find the thermal diffusivity K from this equation, where you can substitute the K prime to be 0.49 here, rho to be the 2.7, and C to be 0.2174, and you should get 0.835 for the K. This is the equation for the explicit method, where we can use it to find the TIL plus 1. And the constant lambda here can be computed by using the K delta T over delta X squared. So you should be able to obtain it to be 0.020875. Previously, based on the initial and boundary condition here, we obtained the temperature at this 6 point for time equal to 0 here. So which is the first point, you have 100 here, and at the middle you obtain 0 degrees Celsius, and in the end of the root you obtain 50 degrees Celsius. Since our delta T is equal to 0.1, so our next time is 0 plus 0.1, where you get 0.1 here, and we are going to find the temperature at all the 6 points, where you can see the temperature at the end of the root is given by the boundary condition to be remain the same as previous one, and at the middle we don't know the temperature. So we are going to find the temperature at these 4 points at time equal to 0.1 second or T1. From here we can find the time index to be 0. So this is our current time index, and this is the next time index, which is L plus 1. So in this case, our L plus 1 is equal to 1. To find the temperature at point 1 first, which is at this point, at time equal to 0.1 second, so we substitute T11 here, where your I is equal to 1, so therefore you can substitute I here to be 1, plus the constant here. So I plus 1 here, you obtain 2 minus with 2. So I here is 1 plus I here is I minus 1 here is 0. And then you continue with the L plus 1 equal to 1, therefore your L will be 0. So you substitute 0 for L. So 0 here for L. With that, you success to obtain this equation. And then after we substitute this information inside, where you get T10 here to be 0, and then T20 here to be 0 also, T10 to be 0, T00 to be 100. So after you substitute it, you obtain the temperature 11 to be 2.0875. We can continue to find the temperature at point 2, which is this point, at time equal to 0.1 second. So by using this formula, your I is equal to 2 here. So you substitute the I to be 2, I plus 1 to be 3, I minus 1 to be 1. So by referring to this equation, okay, we can use these three information to find the T21 here. So after you substitute all the information into this formula to get 0 degrees Celsius, so we know the answer for this one to be 0 degrees Celsius. To find the temperature at point 3, which is over here, we can use this formula, which can be obtained by increase the I to 3. So 3 become 4, okay, 2 become 3, 1 becomes 2. So you get this formula, and then substitute all the information here, you should be able to obtain T31. So after you substitute inside this formula, then you should get 0. So this is the answer for 0 degrees Celsius here. And we can continue for the last case. So to obtain the temperature at point 4 here, so to obtain this temperature, then we need to change the I to be 4. So 3 becomes 4 here, 4 becomes 5, 3 becomes 4, 2 becomes 3. So to get this answer, we need the information here, and you substitute inside this equation, you should be able to get the answer to be 1.04. So with that, we know the answer for this is 1.04. So we success to find the temperature at T equal to 0.1, which is the current time here. And we are going to find the temperature at next time, which is T equal to 0.2. So these are the temperature we are going to find. So to find the temperature at point 1 here, so substitute into the formula, you obtain T12, and when you compare, your I is equal to 1. So with that, you can obtain 1 for all the cases here. And then I plus 1 is 2, I minus 1 is 0. And since L plus 1 is 2 now, so your L will be equal to 1. So you have 1 for your L. Then you substitute all the constant inside. So this is the equation that we can use to find the temperature for 1, 2. And you can substitute the T11 to be this, T11 here, and then T01 substitute inside here, T21 substitute inside here, calculate it, and you should obtain the T12 to be 4.09. And then we can continue. For the rest, using the same method, you should obtain this result. This is the temperature result at T equal to 0.2 seconds. If you continue the calculation, then you should be able to obtain this result, where you can see at the end of the root here, so the temperature always 100, and the temperature here always 50 degrees Celsius. And the temperature at x1, x2, x3, x4 point here is increased over the time. And you can see the temperature at x1 increased faster compared to x4 because the temperature at the boundary condition is higher here.